Okay, so let's talk about the grades that are on the test. So I say this, I'm recording, so if you miss any of the details for how to calculate your grade, just check out the video. I'll post it on YouTube later. On Wednesday, I'm going to come in and ask each of you guys to make a choice as to how you want me to calculate your course grade at the end of the semester. Up here on the top is the syllabus. You have a copy of this. It's also on Moodle. There were 3 different grading options. There's the standard one, there's the test heavy option, and the test light option. And I wanted to make sure you guys had at least seen one of my tests and taken it and gotten a grade on it before you picked which one you thought would be the best for you. So on your paper, where I've got some numbers written in blue, those are your averages for the homework and for the questions of the day and the quiz. And at the moment, it's just the one test. In terms of these numbers, there's a little paragraph that describes how I dropped things. At the end of the semester, I dropped the 3 lowest homework grades. I think it would be misleading to drop 3 homework grades right now because we've only like a third of the way through the semester. So I only dropped 1 homework grade on that one. And the same thing with the daily activities. And I think I dropped like a fraction of a quiz, like a third of a quiz or something. So it's all in the paragraph right below the numbers. To calculate your current average, which is a number that I wrote down there at the bottom, what I did is assume that you guys are going with the standard grading option. So what that means is the homework, which you can see in the standard option is 10%. You take that homework number, you multiply it by 0.10, 10%. You write all the percentages there in purple from the standard option. You'll multiply all those guys across, so you get 4 numbers, and you add them up. Now, normally that would be out of 100. How come it's only out of 80 right now? What exists that you have not taken is the final exam. So even if you had 100 on everything, you'd still only have an 80 right now. So I divide by 80 at the end to make it a percentage. So to make sure you understand what I'm doing later on, multiply everything by the standard grades and make sure you get the number that I put down there at the bottom, okay? And then change it. Change it to test heavy if you're thinking of going that route. Try test light if you're thinking of going that route. You'll get 3 different current averages. And you need to take those numbers and also think about how you are willing to spend the rest of your semester studying and preparing and doing homework or not. And then on Wednesday, you're going to come in and make a choice as to which of those options is the best for you. Any questions about any of that? Eliza, did that answer your question about the dropping? Okay. All right, just in terms of numbers, the high grade on this test was 98, achieved by 2 people. The median grade, what does the word median mean? It means middle, assuming what? It is an average. Yeah, in the middle, but we have to do what before we pick the middle? Right, so assuming that everybody was lined up from the lowest grade to the highest grade, the person in the middle, that's the median, was 86. 86 was the median grade on this test, which is quite good, quite good. All right, so we're done talking about that, and you guys have a new packet on your table, so grab one of those. This is the packet for the middle third of the course. And we'll just take a quick look at the calendar. We just finished test number 1, and that is behind us. And today we start talking about equations of lines. Next class, where you see the word line again, we talk about linear regression next class. And then some different ideas come in before we talk about a real big theme in our class called functions. So that's where we're headed. What's happening here? This is Friday. What's happening Friday? Quiz. It never ends, does it? Pretty much once a week we have something. So we have a quiz coming up on Friday on only 2 sections of material, so it's on a little bit less than the normal quiz is. Any questions on the calendar? Okay. So the first piece of paper in this packet is a reference sheet. You're going to bring that with you to the test, but we'll just skip it for right now, and the back is blank. Hazen. Yeah, let's, can we grab one from over there? Thank you. Okay, and so today we talk about lines. So can we start with Sam, number 1 at the top of page 3? Okay, anything from a prior math class you can just shout out? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, Any other stuff we remember about lines? Point slope. Okay, so apparently there's something called the point slope equation of a line. Other stuff about lines? What is this thing we're calling M? Slope. Okay, so slope is something about a line. What is this V? That's the y-intercept. Okay, good. Anything else about lines that we know? Okay. What do you mean when you say they're continuous, Taylor? We agree. Lines go forever, both directions. I'm going to add one thing to your word continuous. I'm going to say there's also no breaks. Like it doesn't go like this and then like that, right? Like a line is one continuous thing. You could draw it without picking your pencil up off the paper. All right, anything else about lines? Okay, so we will see some stuff about parallel and perpendicular. Okay, so I think this is a good list of stuff about lines that maybe some of us have seen before. We'll go to number 2, Megan. All right, so here's a picture of a ramp, like maybe a wheelchair ramp or something like that. And there are laws about how steep the wheelchair ramp can be, because if it's too steep, then a person can't go up it. So there are laws regarding the steepness or the slope of the wheelchair ramp. So the slope of this ramp is 1/12. I haven't defined slope. I will right below. But to say the slope is 1/12, you can see that that 1, is that a horizontal or a vertical 1? That's vertical. It's 1 foot off the ground. And how long did it take to happen to get that rise of 1 foot? It was 12 feet horizontally. And the slope is the vertical divided by the horizontal. That slope is 1/12. Pitch of a roof, in this case, looks like it's a vertical of 1 and a horizontal of 3, and the slope is 1/3. And I also think there are laws regarding the pitch of the roof, and different pitches accomplish different things. If you're in a place where there's like a lot of snow and ice, you might want the roof to be really steep, so the snow and ice doesn't stay up there, but rather falls off. If you want to live in a place which is really, really energy efficient, I think maybe just like a flat roof, where you don't have that extra space where the heat escapes to and all that. And then one more example, I don't know if you've seen, like pictures of like a truck with a kind of ramp on it. What does that mean? Yeah, there's a percent grade happening here. So they warn truck drivers, hey, there's a really, really steep downhill section coming up. Just make sure your brakes are working, because if they're not, you might be in trouble here. Or there's a really steep uphill section. Why would that be good information for a trucker? Yeah, they got to hit the gas. I mean, it could be. So like in a car, you can pretty much go up any steepness that's out there. But in a truck, if you're not going like at least 40 when you get to the really, really steep part, the truck just might not have enough power to make it to the top of the hill. And so that percentage there, like it might say 8%, which really means 8/100. And it's the same idea. There's a vertical change of 8 feet for every horizontal change of 1 foot. Okay, number 3, Eliza. Okay, a ton of different ways to think about slope. In a nutshell, slope is about steepness. The steepness of a line is something that we assign a number to. It is called slope. What letter do we use for slope? M. We use M every time. I thought I knew why. I'm no longer convinced I know why, but it's M. And it always means the rise over the run. That is the vertical part divided by the horizontal part. Said another way, the vertical part is a change in the Y value. And the run, the horizontal part, is a change in the X value. That Greek letter that looks like a triangle, what is it? That's a delta. delta. And oftentimes delta stands for change in a math class. And in fact, that's exactly how Eliza read it. She read it, change in y. Oh my gosh, what happened? She could have said exit. She could have said delta y, but she read it change in y, and that's exactly what it means. Just a little symbol meaning change. And then finally, we've seen the x2, y1, all that stuff. That's the like real exact formula. If you have 2 points, you throw them into that formula to figure out what the slope is. We'll use that in just a minute. Let's answer this question. What kinds of slopes correspond to uphill lines? Okay, so take a look at the ski, or the, what do we call this person? Rock climber? I thought he was like in a, well, he's all geared up, so I figured he was like snow mountain climber. Ice climber, maybe. Yeah, that sounds like risky. Ice climber. All right, so how much is the run, the vertical part? It's, let's see, so I don't have a number down here, but maybe it's 1 or something like that. And then the rise is 2 in this case. And so the slope of that line, remember it's the rise over the run. That's a +2 over a +1 is +2. It's a positive number is all I want to say about that. But if you got our friend, the downhill skier here, which by the way, that is a crazy slope. That, like, if you were skiing on that thing, that's really steep, isn't it? I mean, I don't ski, but my God. So in this case, if you run, it's still a positive whatever. But if you rise, it's not really a rise, right? Your change in y is a negative number. And so what kind of a slope do you get over there? You get a negative slope. And so so uphill lines mean you are rising and you have a positive slope, and downhill lines means you are falling. But whether you say you are going uphill or downhill depends an awful lot on which way you're headed. Could I not think of this guy as being an uphill line if I were walking that way? It's uphill if you walk right to left, isn't it? Okay, so we need to all agree to walk the same direction, and I will say that everybody in the world decides to walk to the right. So whenever we talk about things being uphill or downhill, we are assuming that we run to the right or walk to the right. So every time we walk on a line, we are going to walk left to right. And then we can talk intelligently about uphill and downhill. Okay? All right, so that's all some kind of descriptive stuff. Let's see if we can do some nitty-gritty, like actual calculation things here. In number 4, we'll go to Connor. Okay, so let's try this one. I'm just going to draw a picture here. You don't need the picture, but I want to make sure you guys see exactly what it is that we're trying to accomplish. So the point 1, 2, let's see, over 1, up 2, so that's right there. And then to say that we have a slope of -3, well, slopes are generally fractions. So if I want that -3 to really be a fraction, -3 over 1, that's the only way to not change it. Right now I've made it a fraction. It's still -3. But now I can talk about it. I can say that this -3 is your rise, and this +1 is your run. So I'm going to start at the point that I've got in red, and I'm going to find a new point. I'm going to run 1, which means which way? Left or right? If we run 1, that's positive. But, okay, at least one person knows we're running right. I need everybody to know we're running right. Where are the positive x's? Where are the positive x's? They are to the right. So when I say move 1 in the positive x, you go to the right. So we run 1. Temporarily, we're going 1 to the right. And then we are rising -3. All right, rise is not the best word there, but I'll use it anyway. But if I say I'm going -3 in the y direction, which way am I going? I'm going down. So we go down 3. So we go down 1, 2, and 3. And I will put a dot on this next spot right here. And I can figure out what that point is. It used to be 1, 2. Can you guys figure out what the new point is? We ran 1 to the right. Yeah, 2 and -1. 1 to the right, so increase the x by 1. 3 down, decrease the y by 3. And if I were to play the same game one more time, I could run 1 to the right and then 3 down, 1, 2, 3. I land on another point. And the idea is that no matter how many times I do this, what's true about all those red points? They're all on the same line. And that's the line that we're talking about here. So what we're after is the equation of that line. Are we okay with that idea of like graphing a line from a point and a slope? That was quick. So let's do the calculation, see if we get what Ira's got. Okay, the only equation of a line that I will ever ask you to use is mx plus b. There is something called point slope, which this table had referred to. I'll write it down up above. I will never ask you to use it, but if you want it, it is y minus y1 equals m times x minus x1. And in fact, I'll even go better than saying I will only require mx plus b. I require you to be good at one of those. You pick. I'm going to use the mx plus b every time. It seems like that is what most students these days are more comfortable with. I think over the course of my lifetime, there has been a change away from this one, because when I was in school, it was always that equation. And over the course of my career, it has gradually become more and more mx plus b, to the point where some people have never even seen the other version of the line, which is okay. So I'm going to kind of go with the crowd and use mx plus b every time. The mx plus b? Yeah. Well, there are fewer symbols in there, but I think it's the same amount of work. But we have to do some work to get b, right? Let's see if we can do it. Okay, y equals, m stands for what? Slope. Slope is given in this problem. It's -3. X is just x, b is b. So I've got that. All we did is change the m to a -3. And then we're going to substitute. We're going to say, okay, this 1 is an x value, and that 2 is a y value. That's an x, and that's a y. And I can take that x and that y and throw it into this equation, and the only letter that will still be there is which one? B. And I'll be able to find b. So let's plug them both in. So this guy becomes, instead of y, 2, the y coordinate, equals -3 times, instead of x, 1. And I can find b. Are there questions on that process there? Plug in the x and the y. Slope is still -3. And then just add the 3 to both sides. And we just figured out that b is 5. And then don't forget the final goal is to write an equation with x and y. Y equals, let's see, it's still -3, x back to x. How much is b? Plus 5. So that right there is the equation of the line. Y equals 3x plus 5. Are there questions on that process? Raise your hand if you've done this kind of process before. Super. Okay, next page. Number 5, Hazen. Okay, this is similar to the previous equation. In the previous equation, I didn't give you 2 points. What did I give you instead of the second point? I gave you the slope, right? Slope was -3. Okay, so what do you do first if you have 2 points? You find the slope. If you can find the slope, then you can repeat the process from the previous problem. Okay, we are going to skip this one. I want to replace that with another question that has a little bit more context than just here are 2 points and find the equation of the line. But try this one for practice. The first step is to find the slope. We'll come back and we'll do an example like that with more context in just a few minutes. Let's jump to 6. We'll go to Joe. Okay, so negative 3, 4. Again, I don't need to plot, but I'll just show you what it looks like. 3, 1, 2, 3, 4. Okay, so negative 3, 4 is that point. And I want the equation of a horizontal line that passes through that point. So I want the equation of that. And it turns out the equations of horizontal and vertical lines are kind of special. They look a little different than the mx plus b that we're used to. So here's the question. Could you guys tell me what are the coordinates of this point right here? So that's negative 2, right? And 4. And what if I were to pick one out here? So maybe like 7, 4, right? Something 4. Every single one of those things has a y coordinate that is 4. That's what it means to be on that horizontal line. So what's the equation of that line? It is y equals 4. It's the defining characteristic of every point on that line. The y coordinate is 4. It looks weird because there's no x's, but what did we discover about the allowable x's here? What x's are allowed? Anything. And it doesn't matter what x you pick, y is always 4. So we're not looking for something like down here, where depending on the x that you pick, there's only one y that's going to be the right answer. Every single point, x, has a corresponding y. It's not that. You can pick any x that you want to. What's the answer for y every time? It's 4. So the equation of that line is y equals 4. And I will say that the equation of every horizontal line is y equals some number. You just have to think about what that number is. And then if we look at the vertical, so a vertical line going through that same red point, let's make up a coordinate down here. All right, let's see. So how much is the x? It's negative 3, and then maybe negative 8, something down there. And what about this point right here? Negative 3 and 0. And what's the defining characteristic for all those points? The x is always negative 3. Doesn't matter what y is, the x has to be negative 3. So the equation of that line is x equals negative 3. You can't know. The only things we can put into the calculator are y equals, and that's one of the weaknesses of the 83. Okay, so that's good. And so then we'll just add here that every vertical line has the form x equals some number. It turns out that you can plot vertical lines on the calculator. You put me on the spot here. Let's see if I can do it. So certainly we cannot go in here and type in x equals 3. There's no way to change it from y1 to something with x. Okay, so this is an opportunity for you guys to watch me fail, maybe. All right, I'm going into mode. I'm changing mode from function to polar. And if you take pre-calculus, you will talk about that mode and what polar means. But if I go into y equals, well, what did it used to say? y1, y2, y3. Okay, so now it's different. It says R1, R2, R3. And normally when I hit this button right here, what does it say? It says X, right? You hit that button, it says X. If I hit this button now, it says theta, which is a different letter. So I think that if I did something like 3 divided by cosine of theta, and just, thank you. So suffice it to say, it is a lot of work to make the calculator graph a vertical line. Okay, good question. 7, we'll go to Surge. Surge, number 7.
Is my window off?
Okay, parallel lines. What can we say about two lines that have the same slope? That's right. If two lines are parallel, they have exactly the same steepness, so the same slope. Perpendicular is more complicated. So we go opposite, and we go reciprocal. Two things, reciprocal. Opposite, reciprocal. So for example, if the slope of one line is 4/7, then the slope of the perpendicular, and I'll write that m perp equals, opposite means negative, reciprocal means flip it over. So given one slope, I would like you to know that fact. Take the opposite, flip it over. Turns out that slope is perpendicular to the first one. Yes, negative is the same as opposite. Yeah, negative reciprocal is good. Okay, can we go to Katrina for number 8? Okay, let's try this one here. All right, so first I'll use letter M for slope. What number in that problem is the slope? 15,260. Slope is always the number touching the x. Now I think it's really, really important to be able to interpret slope. This equation has some context. It has to do with how many doctors there were at different moments in time here in the US. The slope means something. It's not just a number. But I think to get a sense of what it means, it's important to write down the units. If you write the units, you'll be almost all the way to the what does the slope mean. So thinking about the fact that that the slope is the change in y over the change in x, then the units on the top are whatever the units were for y, and the units on the bottom are whatever the units were for x. I think that's probably worth writing down. But the units for the slope are always the y units over the x units. What were the units for the y in this problem? It was the number of doctors. So this is doctors. And then on the bottom, you have the x units. X in this case was years. And so this slope means something. It means 15,260 doctors per year. Okay, probably don't want to write years there, but doctors per year. In this country, we gained 15,260 doctors per year. That's what the slope is. And so we'll write that as a sentence. Certainly on a quiz and a test, I'm going to ask you to do this kind of interpreting. But in the US, we gained 15,260 doctors per year. I said gained. How could I change the equation just a tiny bit to make it we lost 15,000 doctors every year? Yeah, it was a positive 15,000, but if it had been a negative 15,000, then we would say we lost 15,260 doctors per year. They retired or they quit, they did something, they're not doing medicine anymore. Okay, the y-intercept oftentimes has a good interpretation as well. What is the y-intercept in this problem? Okay, so that is the y-intercept. It does not make sense in this case. But let's at least write down a sentence that doesn't make sense. What's the x value if you're sitting at the y-intercept? You guys agree? Like if you just draw a line How much is the x right there? It's 0. That's how you get to be on the y-axis. X must be 0. Okay, so then I can say something like, if x is 0, then the y turns out to be this negative 2,973,000. And now we can write our sentence. What does x represent? Years. So in what year? In year 0, there were 73,000, what? Doctors, that's what Y stands for. It's number of doctors. Okay, so it doesn't make sense. We can't. We can't.
So it's important to note this function is only valid.
Yeah, and that's sort of our bailout as to why why it's okay that that sentence doesn't make sense, is that we recognize this formula is only good in a certain period of time, 1970 to 2000. You plug in something before 1970, you're on your own.
X, such as x is greater than or equal to 1970 and less than 2000.
Right, that's it. So we can write an interpretation, even though the interpretation doesn't make sense in this case. But I'm going to ask you on a quiz and on a test to interpret the y-intercept. And I will tell you now that you will not get full credit if you are missing what number in your sentence. What's important, what's true about every y-intercept? That x is 0. If your interpretation, if your sentence does not have the number 0 in it, you have missed something. 0 is important. Okay, any questions on that? Okay, so here's what I'd like to do. And this little thing might take us about 10 minutes. I've never tried this before, so I don't know exactly how long it will take. But as soon as we finish, the activity is down here, and you'll have lots of practice finding equations of lines. You'll do some parallel and perpendicular and lots of good stuff. But what I want to do is come back to this problem that I skipped. What was the given in this problem? It was 2 points. And then we have to try to find the equation of the line. Okay, we're going to find the slope, and then it becomes like the other problem. We're going to do another example where I give you 2 points and you find the equation, but it's not going to be quite that. So here's what I want to do. This is on my calculator. All right. Let's go back to function mode. Okay. On New Year's, there is a big party over in Times Square. Yes, I've seen it on TV sometimes. And what's the culmination of this party at Times Square? Is the ball drops, right? And Dick Clark is there at 374 years old, whatever old he is, and the ball drops, right? Okay, and so I have a friend who is another math teacher up in Canada. His name is Ron Lancaster, and he was interested in trying to simulate the ball dropping on the calculator. And so he wrote a little program with the help of a friend of his named Chris. And this program I can give you the code for if you're interested. But I typed this program into my calculator, and I will show it to you now here. And it is called years. And that's the first part, which looks like what? Okay, so I've got a platform, got a pole. These are supposed to be the tops of what? Building. So you got to kind of use your imagination. It's a graphing calculator. What do you want? So those are the tops of the buildings. What's going to happen on the pole? The ball is going to drop. What I would like us to do is time how long it takes the ball to drop according to this program. Normally, if your cell phone is out, I yell at you and I say, put it away. But if you have a cell phone on you and it has a stopwatch feature, take it out. I do have 5 stopwatches. If nobody at a table, can you join this group right here? So we have at least 1 stopwatch for every table. There we go. We'll put that here. So find the stopwatch function on your phone if you have one. Otherwise, use at least 1 person at each table should use the stopwatch. Anybody need more time to find the stopwatch thing? We all got it? Okay, so I'm going to say 3, 2, 1, go. And when I say go, lots of stuff is going to happen. When I say go, I'm going to hit the enter key. You're going to hit the start button, and that ball is going to drop. Okay? 3, 2, 1, go. Some of you guys were early. I heard it. When the ball hits the building, it will stop right there at the bottom. Hit the button again when it hits the building. Okay, we all have a time? Everybody have a time? Okay, so here's what I want to do. I want to try to come up with some average because we all have like a different time on there, right? All right, so let's see if we can't find an average real quick. So we come back here and new page there. Okay, so raise your hand if you have a time that you are looking at right now, and we're just going to yell them out real quick. Just go around here. Okay, we'll go back to the corner there. Okay, next corner table. Anybody else? All right, here. Anybody else? Yes. Okay, everybody that has a time, it's up here somewhere. Okay, you can see there is some range. What's the highest number we see? 8.5, the lowest number we see? 8.04. Okay, this is our way, nothing personal. It could be 8.04, I don't know, but we're going to go with the masses here. We're going to cross out the high and the low, and can we get somebody with the calculator to find the mean of the rest of these numbers? We're just going to add them all up and divide by however many you see, and we're just going to call that the time. It's all an approximation, but at least we can get an estimate here. So, yeah. Okay, anybody have an average for me? Okay, a few people said 8.26. You got the same thing? Good. All right, so we'll just average all the times. 8.26 seems about right. Now I put a 15 here, and I put your 8.26 over here in the y. So let's talk a little bit more about this program. And by the way, is that not really cool that the ball drops? And what else happened when the ball hit the bottom? 2012. Come on, that's pretty sweet. Okay, so let's talk a little bit about this program and what's going on in here. So are there any programmers in here? Any of you guys like do any programming? We got a couple of people that do a little bit. So I'm going to not get into all the nitty gritty, but just show you a tiny bit of what's happening in the inner workings of this program. All right, the first line says B is 15. Where have we seen the 15? Yeah, 15 is that number that I put up there. I'll come back to what it is, but anyway, B is 15 for whatever that is. Okay, it does a lot of setup stuff and makes it so that the window isn't minus 10 to 10, but it changes it to something more appropriate for our buildings. What do you think these line commands do? They draw some lines. This is how we draw the building. You take the point 35, 21, that's 1 point, and you take the other point 35, 62, and you connect them with a straight line. If they are both at 35, is this a horizontal or a vertical line? The x coordinate is 35 for both of these points. One vote for vertical. I want other votes. The x coordinate is 35 for 2 points. Is that a horizontal line? Can you guys make one of these? Put one of these up for your votes. You don't get to pick both. Just one. Yeah, this is a vertical line, and that's one of the vertical lines of the building. So it draws all the building stuff, and that's all fine there. Okay, and then it's a pause. That's where it waits for me to hit enter before the ball starts to drop. And then there's this for loop here. And this for loop just says, all right, we're going to start H at the number of 62. I don't know what H is yet. But H is going to go from 62 to 21, and it's going to count by negative ones. So first H is 62, and then some stuff will happen, and then H is going to be 61, and stuff happens, and then H is 60, and stuff happens. And when does it stop? When H gets to 21. So I'm not really sure what it's doing, but at least it's counting down from 62 to 21 and doing some stuff in between. Now we get to that B that I mentioned all the way at the top was 15, just that random thing. This for loop right here has nothing inside of it. It says for and it says end. So basically what we're asking the calculator to do is count from 1 to 15 and then do something. And the something is this stuff down here. This is the drawing the ball. So we tell the calculator, count from 1 to 15, draw the ball. Count from 1 to 15, draw the next ball. Count from 1 to 15, draw the next ball. So why am I doing that 1 to 15? It's to slow the calculator down a little bit. If I ask it to count from 1 to 100, what's going to happen? It's going to slow down even more. So apparently counting from 1 to 15 makes the ball take 8.26 seconds. What we're going to do is we're going to change that. So I'll go all the way back up to the top, and I'm going to say, all right, calculator, I want you not to count from 1 to 15, but count from 1 to 90. So can you guys clear the times that are on your stopwatches and phones? Uh-oh. What is going on here? Exit without saving. Somehow we accidentally changed one of those commands. So let's bring it back. Okay, program, edit. There. Okay, we're going to count from 1 up until 90. Okay, there's my buildings. Again, I'm going to say 3, 2, 1, go. I'll start it, you start it. Ready? 3, 2, 1, go. Here it's counting from 1 to 90 before it draws the ball. Can you see it slower? It's just pausing a little bit longer before it drops the next ball. So again, wait for it to stop and hit that building and then hit the button. Okay. Everybody has a number. Let's find what that number is. Okay, we'll go around the room same as before. So we'll start up here. Whoa. How much? Well, 14.8 isn't looking so good anymore. What happened? Serge? Okay, in the middle here, Connor. All right, anybody else at the middle have a number? Ooh, man. It's supposed to be a safe classroom, but that you got judged right there, my friend. That's all right. 15.6, we missed that one. Okay, and up here in the front? Anybody else that we don't have up here yet? Okay, somebody has to get crossed out, so we will cross out the high and the low. Can you guys average the remaining times? And just call it out if you have an average. Anybody else? Same. Okay, we'll call it 15.76. We're going to put that in the other spot here. 15.76, that's how long that one took. And I put 90. I said calculator count from 1 to 90, and it took longer. It turns out that we can find the equation of a line that hits those 2 points. That's what I'd like us to do. So here are the 2 points. I'll just recopy them down below. 15, 8.26. And 90, 15.76. Okay, so what we're going to do is try to find the equation of the line that connects those 2 points. What's the first thing you need to find if you have 2 points? Let's find the slope. Okay, so we are going to subtract the y's on top, and we're going to subtract the x's on the bottom. Okay, you don't need to do this, but I will just be really clear. I'm going to call this one x1 and y1, and this one x2 and y2, all right? So let's subtract the y's. So upstairs we get 15.76 minus 8.26. Everybody see it? Subtract the y's, divide by. Now we'll subtract the x's. This moment right here is a moment where you can make a mistake. What do I need to put first? We need to put 90 first. Subtract 15. There's not many ways that you can make a mistake on slope, but I just want to tell you about them so you avoid them. Number one, you need to subtract in the same order on top as on the bottom. There's nothing special about calling that first point x1 and y1. I could have called the second point x1 and y1. What's important is that you subtract in a consistent order. If you subtract this guy minus this guy, then when you subtract you must subtract in the same order on the bottom. That's one way to make a mistake, all right? Another way to make a mistake is to accidentally subtract this guy minus this guy. X's and Y's, I will tell you, I have never subtracted X's and Y's. They just don't go together. They say completely different things. One of them is a left-right, the other is an up and down. They're really separate. So there's no reason that we will ever subtract X's and Y's. We need to subtract Y's from each other and X's from each other. There's one last common mistake, and that's to put the wrong thing up on top. Which one always goes on top? Thank you for making the mistake. Like the one that goes on top is the Y, but it's really easy to put an X up there. It's easy. No, that was good. So make sure you put the Y's on the top. Slope has Y on the top. Okay, let's subtract here. Equals, so what do we get on top? Is that 7.5 divided by 75? Okay, it turns out this is quite a nice number. What number is this? 0.1. Perfect. And now that we know the slope, we can go back to our y equals mx plus b. What number is 0.1? Is the m. So we get y is equal to 0.1 x plus b. And now all we need to do is plug in an x and a y into that equation. Which point should we pick? Doesn't matter. You'll get the same b regardless of which point you pick. I'll pick the first one, but it makes no difference. How much is the y coordinate of the first one? 8.26 equals the m is still 0.1. How much is the x? 15 plus the b. $8.26. How much is 0.1 times 15? 1.5 plus the b. So 8.26 subtract 1.5. That is the b. All right, what do we get? 7.26, 6 point. Somebody else help me out here. 76. Is that right? Okay. That is the equation of the line. And I will tell you that that 6.76 means something. Remember the x was me artificially slowing the calculator down by saying count from 1 to x. Count from 1 to 15, or count from 1 to 90 and drop the ball really slow. How much is x if we're thinking about the y-intercept? 0. So if I say don't count from anything, just don't even bother pausing, just draw the ball as fast as you can. What does the 6.76 mean? That's how, I don't want to say how fast, but how many seconds? It will take 6.76 seconds if I don't put in any pauses. That's the fastest it will go. How come it doesn't go instantaneously? It's a little rinky-dink calculator with a few pixels on the screen. I mean, it takes some time to do its calculations and drawing, right? Okay, so last thing I want to do with this equation. It turns out, does anybody know how long it actually takes the ball to drop every year, like in reality? Because they time it. It's not just like a random thing. They set up that ball so it takes exactly 10 seconds to drop every year. And if you sit there with a stopwatch next January the 1st, you will count exactly 10 seconds from the start of the motion until it stops, okay? What do you think I'm going to ask you to find here? We were able to make it take 8 seconds. We were able to make it take 15. Let's make it take 10. So which one is the 10? If I say I want it to take 10 seconds, is that the X or the Y? That's the Y. So we're going to put 10 seconds in here, and you guys need to find the X. Let's try. Again, which one is the 10? 10 is the Y. Equals 0.1x plus 6.76. Can you guys solve that equation with your neighbors? Did I do that right? 32.4? Okay. So what does that 32.4 mean? Yeah, we need the calculator to pause before it draws the ball. We're going to ask it to count from 1 to 32.4. Okay, I'm going to make it 32 just because I need to type in a nice number. And if we make it count to 32, how long should it take for that ball to drop? Should take 10 seconds. Let's try. So get those stopwatches ready. I'm going to make my change here. And we said what, 32? Okay, here we go. Stopwatches ready? I'm going to say 3, 2, 1, go again. You ready? 3, 2, 1, go. Oh, Eric, I don't know if your time is valid now. 9.75, 9.99, 9.6. How much, Connor? Yep, Hazen. 7.94. All right. You're a little bit high. I don't know. It's like, yeah, there's like a Hazen correction factor that like, oh, I see. All right. Any others close to 10? That's close. Okay. So what I would like you guys to do is come back down here. We're on page 4 and see how far you can get on this equations of lines thing. Work through as many as you can do. And I'm guessing there's an answer key if you keep looking far enough. All right.